Welcome back again. We will continue with the link Q class, where we define the secular linked list. If you're using a secular linked list, the effective transfer of an item from the head of the list to the tail of the list can be accomplished by advancing a reference that marks the boundary of the queue. We will next provide the implementation of a secular queue class that support the entire QADC together with an additional method rotate that remove the first element of the queue back to the back. A similar method is supported by the class of Python collection module, which you can see on C++.4. With this operation, a round robin schedule can more efficiently be implemented by repeatedly performing the following steps: define and rotate method. Implementing the queue with a secular linked list. To implement the queue ADT using a secular linked list, we rely on the intuition of the figure 7.7, which the queue has a head and a tail, but with the next element, the next reference of the tail linked list to the head. Given such a model, there is no need for us to explicitly store references to both the head and the tail. As long as we keep a reference to the tail, we can always find the head of the following tail in its reference. Our code in fragment 7.9, we created a class which is secular list for storage, and then we have a class in nested class inside class which is for node, and then the method which is initialize an empty queue, and then we check the size, check if it's empty, and then we create the method first return, but do not remove the first element at the front of the queue, whereas the exception empty if it's empty. And then we have the take element or method remove and return the first element of the queue, first in, first out. That is the empty exception or empty error if it's empty, or do the job. And then we add the element to the back of the queue by using the enqueue method. Then we do the same sequel, do rotate from front element to the back of the queue. If we're running the self.size, if it's greater than 0, we set till to set it to the next old one. The double link list. In a single link, which each node maintain a reference to the node that is immediately after it. We have demonstrated this usefulness of such representation when managing sequence of elements. However, the limitation that stem from the asymmetry of a single linked list. In the opening of section 1, we emphasize that we can efficiently insert a node at either end of a single linked list and can delete a node at the head of the linked list. But we are unable to efficiently delete a node at the tail of the linked list. More generally, we cannot efficiently delete an arbitrary node from an zero position of the list if only given a reference to the node, because we cannot determine the node that it intermittently precedes the node to be deleted, yet that node need to have the next reference update. Provide great symmetry, we define a linked list in which each node keeps an explicit reference to the node before it and a reference to the node after it. Such structure is known as a double linked list. This list allow a greater variety of question time operation, including insertion and deletion at the arbitrary position within the linked list. We continue to use the term nest for the reference to the node that follows another, and we introduce the term prev or prev, which is previously for the reference to the node that has preceded. The header and the tailor sentinels. Sentinel here means the guide. So we have a head which guide from the front and then trailer which guide from the last end. In order to avoid some special cases when operating near the boundaries of a double linked list, it helps to add a special nodes at the both end of the list. A header node at the beginning of the list and the trailer node at the end of the list. These dummy nodes are known as sentinel or guards, and they do not store element of the primary sequence double linked list with such sentinel as shown in the figure 7.10. A double linked list represents the sequence of JK, which is this JFK, another list with this PVD, this is FO, FSO, SFO, and then the front one, which is a dummy and empty, it puts as a header, and then the last one, it puts as a seal. So this check the previous one, they also check to also connect the next one. So it connects on both ends of the side, unlike the single list where it's only go one side. When using a sentinel node, an empty list is initialized so that the next field of the header point to the trailer, and the previous field of the trailer point to the header. The remaining fields of the sentinel are irrelevant, presumable 9 in Python. For a non-empty list, the header's next will refer to the node containing the first real element of the sequencing, just as the trailer previous relevant node as element of a sequence. Advantage of using a sentinel: although you could implement a double linked list without sentinel nodes, as we did with our single linked list in section 7.1, slight extra space devoted to the sentinel data simplify the logic of our operation. Most multi-header and the trailer nodes never change. Only the nodes between them change. Furthermore, we can treat all the insertion in a unified manner because the new node will always be placed within a pair of existing nodes in a similar fashion. Every element that is to be deleted in current it to be stored in a node that has neighbors on each side. For contrast, look back at our linked list, link Q in implementation from section 1.2, it's NQ a method given in fragment 7.8 add a new node to the end of the list. However, its implementation required a conditional to manage a special case of inserting into an empty list. In the general case, the new node was linked after the existing tail, but then adding an empty list, there is no existing tail instead of its listener to reassign head to reference the new node. The use of sentinel node is that implementation will eliminate the special case as they always been an existing node. Inserting and deleting with a double linked list. Every insertion into our double linked list representation will take place between the pair of existing nodes. A diagram in figure 7.11, for example, when a new element is inserted at the front of the sequence, we will simply add the new nodes between the header and the node that is currently after the header. So any new node that's being added or put are going to be between the trail and the header. So adding a new one, we check, okay, now we make it from here, we put it here, and then the list is added. Adding element to a double linked list with header and trailer sentinels before the operation, and B, after creating the new list. And then in C, after linking the neighbors to the new list. So moving to the same thing, adding element to the find of sequence C represented by a double linked list with a header and a tailor sentence. A for the operation, B after creating the new list, new nodes, and then C after the linking of the neighbor to the new nodes. The deletion of a node portrayed by the figure 7.3, they didn't put it in the opposite fashion of insertion. The two neighbors of the node to be deleted are linked directly to each other by passing the original node. As a result, the node will no longer be considered part of the link of the list, and it can be claimed by the system garbage collection. Because of our use of Sentinel, the same implementation can be used when deleting the first or the last element of the sequencing, because even such an element will be stored at a node that's between the two nodes, between the two others. Before remove the element, removing of the element PVT, then from the linked list, and then before being removed after the link out after remove, then after being removed. The basic implementation of a double linked list, we begin by providing a preliminary implementation of a double linked list in the form of a class name underscore double link base. We intentionally named the class with a leading underscore because we do not intend it to provide a coherent public interface for general use. We will see that the linked list can support general insertion and deletion in a constant time with keys operation, but only if the location of the operation can be successfully identified with array-based sequencing and index. An integer index was a convenient means for describing a position within the sequence. However, an index is not convenient for linked list. There is no efficient way to find the element. It will be seen to require a traversal of a portion of the list. When working with a linked list, the most direct way to describe the location of an operation is by identifying a relevant node of the list. However, we prefer to encapsulate the inner workings of the data structure to avoid having users the access node of the list. In the remainder of this chapter, we'll develop two public classes that inherit from our double link list. Our low-level double link list case relies on a series of non-mapping nodes class that is similar to the one for the single link we were given in the previous section. So that double linked vision provides the previous attribute, and in addition to the next an element attribute. This is the class nodes. Previously, it had, I think, it had only element. Now it's got previous and the next, because now it's double, the double linked list. Using checking on a double linked list, we have a class which is double linked list. The class nodes, similar that we just shown like before, and then we have a method in it, initialize an empty list, and then a length list, checking the length of the list, and then an empty, check if it's empty, and then we have inserts between, and then there's a predecessor and a successor, adding element E between the two existing nodes and return the new nodes. And then we have a method deletes the nodes, deletes a sentinel nodes from the list and return its elements running from the predecessor successor is next predecessor, and then you assign the next to the successor, assign the successor becoming the previous, then become a predecessor, and then you minus 0 by 1. The element, we assign the element to the node when the element has decreased, when the nodes have been removed, and then assign to the next to identified among the nodes. The other two methods of our class are the non-practice utility in set between and delete nodes. These provide a generic support for the insertion and deletion respectively, but require one or more node references as the parameters. The implementation of the insert between method is modeled upon an algorithm that was previously featured in figure 7.11. It creates a new node with a node is field initialized to link to the specified neighboring nodes. In the link, the field of the neighboring nodes are updated to include the newest nodes in the list for its convenience. The node returns a reference to the newly created node. Implementation of the delete nodes method is modeled upon the algorithm portrayed in figure 7.18. And the neighbors of the node to be set are linked directly to each other, thereby bypassing the deleted node from the list. As a formality, we intentionally reset the previous nest and element field to be deleted nodes will be none after recording the element to the return. Although the deleted node will be ignored by the rest of the list, setting it field to none is advantageous, that it may help Python's garbage collection since unnecessary link to the other nodes and the stored elements are eliminated. Implementing a deck with a double linked list, the double-ended queue known as deck or pronounced as deck ADT was introduced in the previous session with an array-based implementation. We achieve all operation in a Mortar's sequence time or the big O of 1 time operation due to the opposing limit to resize the array. With the implementation based upon double linked list, we can achieve all deck operation in the worst case in the worst case time at constant time. We provide an implementation of a linked deck class in the following code segment. Inherits from the double linked list class of the preceding section, we do not provide an explicitly initialized method for the linked deck class as the inherited version of the method suffices to initialize a new instance. We also rely on the inherited method length and empty in the meeting of the deck ADT. With the use of SingleNet, the key to our implementation is to remember that the header does not store the first element of the deck. It is not just after the header that stores the first element, assuming that the deck is an empty list. Similarly, the node just before the trailer stores the last element of the deck. We use inherited insert between method to insert at either at the end of the deck to insert element at the front of the deck, replace it immediately between the header and not just after the header. An insertion at the end of the deck is placed immediately before the trailer. Note that these operations succeed even when the deck is empty. In such situation, the new node is placed between the two sentinels. When deleting element from the empty deck, we rely upon the inherited delete node method. Using the linked dates, we run the first method, which is check if it's empty, resists the empty exception. We run the last, we check if it's empty, resist the first empty, or otherwise return the tailor. We insert the first one, and then insert the last one. We add the element at the back of the queue. Delete the first, we remove and return the element from the front of the deck. We remove the last one. We raise the empty, exception if it's empty. And then we go to section 4, the positional list. ADT, the abstract data types that we have consider this fine, namely the stacks, queues, and deck, or double-ended queues. Only allow update operation that occurs at one end of a sequence or the other. We wish to have a more general abstraction. For example, although we motivated the first in, first out, or FIFO semantics of a queue as the model for customers who are waiting to pick with their customer service representative, who are waiting to speak with their customer service representative, or friends who are waiting in line to buy tickets to show. The queue ADT too limiting. What if a waiting customer decides to hang up before reaching the front of the customer service queue? Or what if someone who is waiting in line to buy a ticket allows a friend to cut into the line position? We would like to design an abstract data types that provide a user way to refer to elements anywhere in a sequence and to perform arbitrary insertion and deletion. When working with the array-based sequences such as Python list, integers, indices, index, provide an element means for describing the location of element or the location at which an insertion or deletion could take place. However, numeric indices are not a good choice for describing position within a linked list because we cannot efficiently access an entry knowing only in its index. Finding an element at a given index within a linked list requires a traversing a linked list, increasing from its beginning or end, counting element as we go. Furthermore, indexes are not good abstraction for describing localization in some application because an index of an entry shapes changes over time due to insertion or deletion that happen in sequences. It may not be convenient to describe the location of a person waiting in line by knowing precisely how far away that person is from the front line. We prefer an abstraction as characterized in figure 14, in which there is some other means for describing a position. We then wish to model situations such as when identified person leaves the line before reaching the front, or in which a new person is added to a new line immediately, then another one. As another example, a text document can be viewed as a long sequence of character. A word processor uses the abstraction of a cursor to describe a position within a document without explicit use of index, of integer index, allowing operations such as delete the character, the cursor, or insert a new character just after the cursor. Furthermore, we may be able to refer to the inherent position within a document, such as beginning of a particular section without relying on a character index or even a section number that may change it as the document evolves. Note the reference as position. One of the greater benefits of a linked list structure is that it is possible to perform constant time insertion and deletion at a arbitrary position of the list, as long as we are giving a reference to a relevant node of the list. It is therefore very tempting to develop an ADT in which method. In its notes, reference several the mechanism for describing the position. In fact, our doubling list in the previous class 7.3, 8.1 has a method that sets the between and delete node that accepts node reference as parameters. However, a direct use of nodes will violate the object-oriented design principle of abstraction and encapsulation that were introduced in chapter 2. There are several reasons for prefer that we encapsulate the nodes of the linked list for both our sake and for the benefit of the users of our abstraction. It will be simpler for our users of our data structure if they are not bothered with unnecessary details of implementation, such as low-level manipulation of nodes or our reliances in the use of sentinel nodes. Notice that to use the insert between method of our doubly base class to add a node at the beginning of sequencing, the header sentinel must be sent as parameter. We can provide a more robust data structure if we do not permit user to direct access or manipulating the nodes. In that way, ensure that user cannot invalidate the consistency of the links by mismanaging the list. Linking of nodes or more problem arises if a user will allow to call the insert between or delete nodes method of our doubling base class, saying a node that does not belong to the given list as a parameter. Look at the code that we see. By better encapsulating the internal details of our implementation, we have a greater flexibility to redesign the data structure and improve its performance. In fact, with well-designed abstraction, we can provide notion of a numeric position, even if we're using an array-based sequence. For this reason, instead of relying direct to node to introduce an independent position abstraction to denote the location of an element within a list. The position list abstraction is ADT or abstract data type to provide a general abstraction of a sequencing of elements with an ability to identify the location of elements, and we define a positional list ADT as well as simpler position abstract data types to describe a location within a list and act as a maker or token within the broader positional list. A position P is unaffected by changes in a list. Only way in which a position becomes invalid is if an explicit command is issued to delete. A position instance is simple object supporting only the following method. We have a p.element, which is the returned element stored as position P, and then we have l.first return the position of the first element of L, or 9 if it's empty. The l.last return the last position of the element L, or 9 if it's empty. L.before element P or parameter P return the position of L immediately before the position P, or 9 if P is the first position. After P return the position of element after position, or 9 if the P is the last one. L.empty return true if the list L does not contain any elements. And then we check the length or return the length size. We iterate. We do iteration or kind of a loops of elements in the list. These are positional lists, including the following updates methods. We had L dot at the first, insert a new element E at the front of L, L dot at last, E of E, insert a new element E at the back of L, L L dot add underscore before P and E, insert a new E just before the position P, insert after, insert a new element after the position P, L dot replace the element, and then Alt delete to remove or delete the element. Note that the first and last method of the position list return the associated position, not the elements. This is contrary to the corresponding first and last method of the text editing. The case.adt, while the case is none, print the case.element. Print the elements to the position, and then advance to the next position. The following table shows the series of operation in initially empty position. List L. To identify the position instances, we use the variables such as P or Q for ease of exposition when displaying the list content. We use subscript notation to denote each position. These are operation methods, returning the value, and then the list position, which is we will use the subscript, the P is under the number. The Doubly list implementation in this section, we presented a complete implementation of a positional of the positional list class using a Doubly list. We rely on the Doubly list base from the section or from the previous section of our low level or representation. The primary responsibility of a new class is to provide public interface in accordance with the positional list. Editing. We begin our class definition in the code fragment 14 with the definition of public position as within our positional list class. The position instance will be used to represent each of element in the list of various positional lists may end up creating redundant position instances that reference the same lying nodes, e.g. when and last are the same. For that reason, our position class define the EQ method and E special method so that it says such as is P equal to Q revert to true when the two positions revert to the same nodes. The validating of position each time a method positionally each class accepts a position as a parameter. We want to verify that the position is valid, and if so, we determine the underlying node associated with the position. This functionality is implemented by a non-public method named underscore validate. Internally, a position maintain a reference to the associated node of list and also reference to the list instance. To assess and update and update the method, the access method of the positional list first are given in a code in a code fragment 15, and the update method are given in a code fragment 16. All of these methods trivially adapt the underlying linked list implementation to support the public surface of the positional list editing. Those methods rely on the validate utility and unwrap any position that is sent. They also rely on the make underscore position utility to wrap. Note as the position instances to return to the user, make sure that never to send a position referencing the sender. For convenience, we have overridden the inheritance underscore insert between utility methods so that ours return a positional associated with the newly created node, whereas the inherited version change node is safe. The problem positional list, we call the class double linked list is a special positional element allowing a positional class creates a position nested position list, and after representing the location of a element, we initialize method considered in constructor should not be invoked by user. Then we have an element returning that is stored at this position. We have a method EQ, special method EQ, returning true if other is a position representing the position. And then we have an E, return true, other it does not represent this position. And then we have a validate, return position node or raise appropriate error if invalid. Make, and then we have a method called make position, return the position instance for given nodes or none if sent enough. Then we have the first, the last method, and before method. Then we have the after method, iteration, the generate forward iteration of the element, the list. And that the end of each a positional list class based on a double link list. And then we have inserts between, where we have parameters such as self, the constructor, and the element E, the predecessor and a successor. At the first one, at the last one, at the before one, and the after one. Those are methods. And then we have the delete, remove, and return the element that's set in position or position P. And then we have a replace, which is as a replacement with the position P with E. And then we assign original or the value to the original element to the E, and then we return the auto value when we replace using this replace method. Sorting a position list. She got 1 minute left, so I'm not sure. Should we continue? We introduce the insertion sort algorithm in the concept of array-based sequencing. This section will develop an implementation that operates on a positional list, relying on a high level in which each element is placed relatively to a growing element, collection of previous sorted elements. We maintain a variable named anchor that represents the right position of the current sorted method. And process position of the list during each pass, which the position just pass the marker as the pivot, and consider where the pivot element belongs to the sorted position. Okay, we can continue maybe after this, just to finish, because I think only sessions 6 and 7 are left. Which when I come back, I'm gonna start from this position, sorting a position list.